Okay, Vijay is going to continue his story about factorization and norms, and he'll explain it all. It will be somewhat self-contained, and those who don't remember or don't, in short, ask questions. Yeah, Vijay, go.
Great, thanks, Avi. Yeah, so as Avi said, this is actually a continuation of a talk I gave last week. So I apologize to anyone sort of coming to this part for the first time. Some of the context might be missing, but I'll try and make the parts of things I present today self-contained. Okay, so I'll start by sort of recapping what we did last week for the first 20 to 30 minutes. Okay. Before that, we require a lot of preliminaries. Again, mostly recapping. So all norms are in this talk are over Rn or R to the n cross n. So either the space of n cross n matrices or n-dimensional Euclidean space. Okay, and there is this well-known correspondence between origin symmetric convex bodies and norms. Okay, so the unit ball of a norm X, is denoted by Bx, and of course it's defined as the set of unit vectors in that norm X such that norm of X is at most 1. Okay, so this is how you go from a norm to an origin symmetric convex body. Okay, and the way to go in the reverse direction, given an origin symmetric convex body, you define a norm as the minimum scaling of the body that contains the vector. Okay, so given origin symmetric convex body, B, the Minkowski functional of B, or like a norm we can define induced by B of a vector X, is defined as the minimum lambda such that X over lambda is inside the body B. Okay, so the minimum scaling of the body that contains X. Okay, right. Yeah, and we'll define the polar of a set. Okay, so for a set S, a subset S of Rn, we define the polar denoted by S circ as the set of vectors Xi such that Xi inner product X is at most 1 for all X in S. Okay, and the usual bipolar theorem for origin symmetric sets. So if S is origin symmetric, the bipolar theorem states that S polar polar is equal to S. Okay, this is a simple consequence of the Hahn-Banach theorem. Okay, right. So we'll also require the definition of a dual norm. So given a norm X, we denote the dual norm by X star. That might not be very legible, I guess. X star, and it's defined as the dual norm of Xi is the maximum such that X is in the capital X unit ball of Xi inner product X. Okay. Now, if we look at the unit ball of this X star norm, one can easily check that the unit ball of the X star norm is just the polar of the unit ball of X. Okay, and now by the bipolar theorem, applying it on both sides, we obtain that the polar of the dual unit ball is equal to the unit ball of X. right? So in particular, this implies that x star star is equal to x. Okay. So if I take dual twice, I get back the same norm. Okay. Right. Now we're coming to one of the central definitions of the talk, which is operator norm, which we'll also refer to as bilinear maximization. And and it's defined as follows. So given a linear map, A from a norm space X to a norm space Y. So we assume X and Y are both over Rn. Okay. We define the operator norm of A as the maximum amount that A stretches an X unit vector, where we measure the stretch in the destination norm Y. Okay, so stated algebraically, this is the maximum of X belongs to the ball of capital X, the Y norm of AX. Okay. Now, simply by the definition of dual norm from the previous slide, this is equal to maximum of X in BX, Z in BY star of Z inner product AX. Okay. And therefore, we actually see that the operator norm has a bilinear maximization formulation. Okay. And let's derive some more equivalences. So this is in turn equal to maximum over X and Z, in the same thing, BX, BY star of A transpose Z inner product X, right? Which, by definition of the operator norm is actually nothing but the Y star to X star operator norm of A transposed. Okay. And it'll be convenient to develop separate notation for the operator norm version, just to type check in various parts of this talk. So I'm going to give separate notation for the bilinear maximization variant of the problem. So I'll denote it by EF, given norms E and F. The bilinear maximum of an n cross n matrix A is defined as maximum little e belongs to the unit ball of capital E, little f belongs to the unit ball of capital F, E inner product AF. This is mostly the definition we'll work with. Right, and it's easy to check that this bilinear maximization for any choice of norms E and F is a norm on the space of matrices A. Okay, it satisfies triangle inequality, homogeneity, etc. Okay, so therefore we can actually take a dual of this norm in the space of matrices. Okay, and it'll be convenient for us to understand what this dual is. And the dual actually comes up very naturally. So it comes from the following equality. We can relax the maximum from being over the Cartesian product of BE and BF to the convex hull. So we can relax it to consider matrices in the hull of EF transpose such that E is in BE, F is in BF. Of A inner product N. Okay, because it's a linear function, maximizing it over a set or the convex hull of the set doesn't change the maximum. So this equality holds. Okay, we didn't do anything special there, right? But now we notice that this set, this hull of EF transpose, so the hull of unit vector outer products is an origin symmetric convex body. Okay. Therefore, this must be the unit ball of the dual norm of bilinear maximization, right? So we have hull of EF transpose such that E is in BE and F is in BF is equal to B of, I should give it some name, I guess the bilinear maximization EF norm star. That is, it's the unit ball of the dual of that norm. Okay. So now that we have figured out what the unit ball of the dual norm looks like, we can also figure out what the dual norm looks like by applying the correspondence from earlier. Just this like minimum scaling of the body that contains a vector. Okay. It turns out that the norm will look as follows. So for a matrix A, we, I mean, in the literature, this is referred to as the projective tensor norm and denoted as E tensor hat F. I'm not going to use this notation again today. I'm just giving this for completeness. Okay. So the projective tensor norm, which is the norm corresponding to the unit ball I wrote above, is given as follows. It's the infimum over all finitary decompositions, summation EI FI transpose is equal to A of summation EI E norm FI F norm. Okay, this, yeah, I mean, for all practical purposes, I encourage people to think about the unit ball and not the norm itself, because it's a mouthful. But really, the unit ball arises very naturally. It's just the convex hull of unit vector outer products.
So Vijay, maybe it's good to, I mean, just a simple example. Let's say when E and F are both L2, then this norm is just I guess the top singular value of the.
Right. Yeah. So let's do examples. Right. So let's say E equals F equals L2. Well, the first thing is that the bilinear L2 norm of A, which is equal to actually the L2 to L2 operator norm of A, equals the maximum singular value of A. Okay. On the other hand, the projective tensor norm, so E tensor, L2 tensor hat L2 is what's known as the nuclear norm. It's the summation of the singular values of A.
So this duality is very similar to the duality between L1 and L infinity, but in the matrix. Yeah.
Exactly. So this is actually this is Schatten norm duality. That is, if you apply a symmetric norm to the spectrum of a matrix, the dual of that norm is the dual norm applied to the spectrum of the matrix.
Okay.
Okay. So yeah, two examples there. Right. Yeah. Okay. And yeah, just you know, just to reinforce what I said earlier, this set hull of EF transpose such that E is in BE, F is in BF, is the polar of the set of bounded bilinear forms. Okay, so it's the polar of the set A in Rn cross n, such that bilinear maximum of A is at most 1. Okay, and if I put the circ on the left and remove the circ on the right, the same fact is true just by the bipolar theorem. Okay, good. Right. Yeah. So now I'm going to define a related but more general optimization problem. or quadratic maximization. Okay. So very similar to the bilinear case, we are given a norm X and we define Q max X of A, given an n cross n matrix A, as maximum little x in the unit ball of capital X of X inner product AX. Okay. For convenience later in the talk, I'm probably going to drop the max and just write QX of A. Okay. I just use Qmax to be consistent with the previous talk, but I'll be writing this symbol so many times that perhaps it's convenient to just write Qx of A.
And without loss of generality, we can assume A is symmetric if you want.
Yes, yes. As Avi said, but if you have an asymmetric, not symmetric matrix, you can average the matrix and it doesn't change the value. So yeah, let's always assume that A is symmetric. Okay, good. And so again here, let's just check that QL2 of A is the maximum of 0 and max eigenvalue of A, which I'll denote as lambda max of A. Kind of abusing notation a little bit. This is essentially the maximum eigenvalue of A, except if A is negative definite, then instead it will be 0. The only reason for this is that we allowed 0 to be plugged in, right? Because 0 is inside the unit ball of L2. Okay, so it's advisable to contrast this the L2 case here with the L2 case in the bilinear version, where for a symmetric matrix A, the maximum singular value is the maximum magnitude eigenvalue, right? Whereas the quadratic maximum is the maximum eigenvalue. So there's the subtle difference between the two quantities. Okay. And I said quadratic maximization is more general. It can be seen as more general using the following. I mean, it's more general in the following sense. So if I take the matrix A to be half times 0, 0, B transpose B, then it's easy to check that whenever I plug in a 2n dimensional vector, let's say E comma F transpose A E comma F, I get back E inner product B F. And so using this fact, you can see that the quadratic maximum of B E cross B F, that is the norm corresponding to the Cartesian product of those sets of A, is equal to the bilinear maximum E comma F of B. Okay. The norm corresponding to the Cartesian product of two unit balls it's simple. It's the maximum of the E norm and the F norm. So it's also a norm. So it's the maximum applied where E norm is applied to the first part E and the F norm is applied to the second part F. Okay, right, so that's quadratic maximization. Finally, we arrive at the definition of factorization norm.
You want to say something about the complexity of these problems even for?
Right, yeah. So for anyone who perhaps missed the previous talk, one of the big motivations for this work was trying to find approximation algorithms for quadratic maximization, which it turns out is closely related to a property of the norm X called the type 2 constant. But yeah, so today I'll focus exclusively on factorization theorems, which do have some algorithmic applications for us. But for today, I'll just keep the talk exclusively mathematical. Right. Yeah. So factorization norm. So we start with a simple observation. So let B map, let's say, space X to a space E, and let C map a space E to a space Y. Then one can check that C times B, X to Y operator norm. Okay, I flipped things around, so maybe let me fix that. Yeah, the operator norm of B times C is at most the operator norm of B times the operator norm of C. That is B e to Y times C X to E. So the proof of this is simple. The maximum amount that B times C, the composition of B and C, distorts an X unit vector measured in the Y norm can be upper bounded by the maximum amount that C distorts an X unit vector measured in the E norm times the maximum amount B distorts an E unit vector measured in the Y norm. Okay, so this is just, I said it in words, but one can just write down two inequalities and it's exactly that. Okay. So we have this trivial inequality. Now the factorization norm, the gamma 2 norm of a matrix A is defined as the infimum over all possible factorizations, BC equals A, of the 2 to Y norm of B times the X to 2 norm of C. Okay. So this is the definition of the factorization norm. And the factorization theorem is a theorem of the following type. It says that the operator norm of A, which is clearly upper bounded by gamma 2 of A. Okay. Gamma 2 of A is the best possible upper bound one can get by factorization through L2. And yeah, so a factorization theorem is a statement of the form, you know, this gamma 2 of A is at most some constant K depending on the norms X and Y times, again, the operator norm of A. Okay, so we're interested in what norm spaces, for what norm spaces can we say that the factorization norm is very close to the operator norm. And it'll be, I mean, often it's good to have K being independent of the dimension of X and Y. Okay. So last time I stated 4 factorization theorems. Okay. Just to give people a heads up, there are many variants of this factorization norm, and they're going to appear in the theorems that I'll state shortly. Yeah, this is just one possible factorization norm. Okay. And actually, before I move on, let me just also note a trivial observation. Gamma 2 of A can also be written as infimum of B, G, C equals A, B, L to N to Y, G, L to N to L to N, C, X to L to N. Okay. The proof of, you know, this two-way factorization being equal to the three-way factorization is very simple. For one direction, you just substitute G as the identity matrix, and for the other direction, you just consider the substitution. You know, B goes to B and C C gets GC, something like that. Okay. Okay, so now let's state the factorization theorems that I'm interested in. Okay, so Grothendieck proved a factorization theorem for L infinity. So he proved that there's an absolute constant such that a certain factorization norm that is even stronger than gamma 2 I defined above approximates the operator norm. Okay, so he actually proved the following. Grothendieck factorization. He proved that for this it's more convenient to use the bilinear versions. The bilinear maximum, L infinity in n dimensions, L infinity in n dimensions of a matrix A, is at most the infimum over all factorizations D1, B, D2 equals A of B1 2 to 1 norm, B 2 to 2 norm, B2 infinity to 2 norm. And this is less than or equal to some absolute constant times the bilinear maximum infinity of A, which, as a reminder, is equal to the infinity to 1 operator norm of A. These two things are equal. Okay, so and yeah, sorry, I forgot to mention D1 and D2 are diagonal. Okay, so Grothendieck not only, he not only showed that the best possible factorization is a good approximation to the operator norm, he showed that you can even take D1 and D2 to be diagonal matrices. Okay. Assuming we're in the situation where X is the L infinity norm. This is something very special about the L infinity norm. Okay. Now PCA showed a much more general factorization theorem that generalizes Grothendieck's theorem.
Just to read it, the Grothendieck factorization again. I mean, if we want to know the best infinity to 1 norm of a matrix, we can scale the rows and columns, right, by constants in the best possible way, and multiply, I guess the max. What do we do with the scalars? I'm not sure, but anyway, and
you're making a good point. Let me
singular value of the top singular value of B. So there is okay.
So that's a good point. Let me state it that way. So another way to state it, which is perhaps nice in some sense, is that for any matrix A that you want to maximize over the hypercube, there exists a diagonal rescaling of the rows and columns, a normalized diagonal rescaling of the rows and of the columns, such that if you compute the max singular value of this rescaled matrix, this approximates the maximum over the hypercube. So the maximum over the sphere of a rescaled matrix approximates the maximum over the hypercube. However, there is some technical condition. So for any A, there exists A tilde where the reweighting satisfies the following condition. So if U is the vector reweighting the rows of A, then sorry, I need to be careful here. If 1 over U1, 1 over U2, till 1 over UN is the vector vector reweighting the rows of A to get A tilde, and 1 over V1, 1 over V2 till 1 over Vn is the vector reweighting the columns of A to get A tilde. These satisfy the additional property that the L2 norm of U is at most 1 and the L2 norm of V is at most 1. Okay, so there is this like normalized diagonal rescaling of A, such that after this rescaling, you can just compute the maximum singular value and it gives you the maximum over the hypercube. So this is what Avi was going for, I believe.
Yeah, and I wanted to see the the bound on the diagonal. So U and V are the diagonals of D1 and D2.
Yeah, exactly. The inverse. Yeah.
The inverse. Sorry, yeah.
Actually, sorry. As you said, yeah. D1 is the diagonal matrix of U, and when you take the inverse, you'll get the reciprocal.
Right. Yeah.
So A tilde is D1 inverse A D2 inverse.
Mm-hmm.
So A tilde is D1 inverse A D2 inverse. D1 is diag of U. D2 is diag of U. That is the diagonal matrix with U and V on the diagonal matrix. Okay. Good. Right. Yeah. So now PCA proved a much more general factorization theorem, which I'm not going to define all the norms for which this holds. I just want to state the factorization theorem. So he shows that if you don't want this additional diagonal factorization, you're happy with any factorization through L2. This holds in much more general settings, and you can show gamma 2 of A is approximately operator norm of A up to some constant k x comma y that depends only on cotype 2 constants of x star and y star. Okay, I mean, defining this will take me beyond the scope of what I wanted to do today. But just know that this in particular recovers Grothendieck's theorem if you only cared about factorization through L2 and not this additional diagonal matrix property. Right? And the other benefit you're getting is that it holds in much more general settings. Okay.
Vijay, can you say a word or two about when you have an approximation like this, what are you thinking of as easy to compute, and what are you like? What is the harder one that you're trying to approximate?
Yeah, good question. Yeah, so in the Grothendieck setting, it turns out that this factorization norm can be computed exactly. And therefore, this immediately gives you an algorithm for approximating the bilinear maximum. Okay. In the PCA setting, which is like this, the usual gamma 2 norm. So without these diagonal matrices, this is not computable in general. And actually, sometimes it's not even approximately computable. However, yeah, I mean, sort of in studying when it is computable, we obtain new algorithmic results. So we are still thinking of this factorization as a good intermediary to try and compute in order to approximate the bilinear maximum. And yeah, this relates to the algorithmic applications of these things.
But I guess I don't know what Cynthia meant in her question, but maybe that where the problem at hand is NP hard, right? It's maximization over the cube. And the factorization lives in spaces, I mean, where they can be computed by convex programming, like semi-definite programming. So that would be easy, up to some constant factor. I guess that you just want to relax this type of problem, to convexify it somehow. I mean, it's not obvious from what Vijay said so far, but some of it he said last time.
Yeah. Thanks, Avi. Right, so yeah, so PCA proved this more general theorem, and both Grothendieck's theorem and PCA's theorem have two components. Okay. So the proof has two components. The first is maximization reformulation of gamma 2 of A, or in the case of Grothendieck's factorization theorem, a reformulation of this infimum D1 B D2 equals A of D1 norm B norm D2 norm. I'm dropping the subscripts just for shorthand. Okay.
Can this be viewed just as a duality theorem?
Yes, yes. So exactly, yeah. So this is some type of duality statement. And the second ingredient is, is an inequality relate maximization to the original objective, which is the bilinear maximization, bilinear maximum, or the operator norm, in other words. Okay. Now, this second step typically involves a rounding algorithm based on Gaussians. Based on sampling Gaussians. And this is what I talked about last week. Okay, so I'm not going to talk about two today because I talked about it a lot last week. My hope was to give sort of a sense of all of the ideas that go into the proof of a single factorization theorem. And so today, I'm just going to prove one, or give an almost complete proof of one for an appropriate factorization theorem. Okay, so just before that, I want to give some, a little bit of bibliographical discussion. Right, so there is rounding, then there's duality, these two steps, and so there's Grothendieck's factorization theorem, where the duality step was originally proved by Grothendieck within factor 2. And Peach showed it exactly. Okay, and it was noticed much later independently by Trop and Nesterov that this duality can be proved using semi-definite programming duality, something well studied in the optimization literature. Okay, Grothendieck and Peach's proofs both were also separation arguments, but they were separation arguments taking place in R to the R to the n. These arguments aren't long, but one difference between these arguments and STP duality is STP duality takes place in Rn cross n. And one consequence of this is sort of an algorithmic statement that comes alongside the result of Trop and Nesterov. That is, you can actually compute these factorizations if you can compute some other associated quantity. Okay. So yeah, I mean, I wouldn't go so far as to say that the proofs are simpler in the Trop and Nesterov case, but they perhaps are more intuitive in my opinion, and often have this algorithmic consequence. Okay. So similarly, PCA's factorization theorem has a rounding step, and it also has a duality step due to Moret. And what we do is we actually show that this duality statement can be reproved using conic Lagrangian duality. Okay, in a sort of generalized fashion to the STP duality earlier. Okay, Yeah, and we actually use this conic Lagrangian duality proof to obtain what we think is a previously overlooked factorization theorem for quadratic maximization. So we get a quadratic version of PCS theorem, which I'll state below. So we show formally that the infimum of B transpose C B equals A, given a symmetric matrix A of B transpose 2 to X star norm times lambda max of C times B extra 2 norm. This quantity approximates the quadratic maximum Qx of A within some constant Kx that depends only on the type 2 constant of X. Okay. I just want to remark that this lambda max of C should be thought of as a replacement of the 2 to 2 norm, so the maximum singular value. So the maximum singular value in the quadratic maximization case became now the maximum eigenvalue. Okay. Right. Yeah. So we prove this theorem, and actually one nice aspect of it is that it's in some sense simpler. So the rounding step here is much simpler. Whereas the rounding step in Grothendieck's theorem and PCA's theorem are both nuanced. Right. And similarly, I cooked up a toy example, a quadratic version of Grothendieck's factorization theorem, for the sake of just showing things in the stock. And again, the rounding algorithm here is simpler. But the duality statement here is very similar to Grothendieck's duality statement. And the duality statement we need for the quadratic PCA theorem is very similar to Moret's duality statement. Okay. So what I'm going to show you today is a full proof of this, the duality statement in this quadratic factorization theorem. Okay, and all the other 4 duality statements, the proofs are extremely similar to this. And given time, maybe I'll indicate how they can be concluded. Okay. Yeah, just to state the quadratic Grothendieck factorization theorem. Sorry. So the quadratic Grothendieck factorization theorem says that B transpose CB, there's no need to transpose if it's a diagonal matrix. B is diagonal, but I just wrote it there to syntactically resemble the quadratic factorization theorem. B transpose 2 to infinity, sorry, 2 to 1 norm times lambda max of C times B infinity to 2 norm. This quantity approximates the quadratic maximum of A over the L infinity ball within a factor of log n. Okay. Yeah. Now, last week I showed Grothendieck's rounding algorithm, and I showed a rounding algorithm for quadratic Grothendieck. Yeah, this week I want to show the duality side. So yeah, as I said, I'm going to show this most general duality statement, the quadratic version, and I'll probably indicate, if time permits, how to derive all the others. Okay. Okay, good. Right. So So as I advertised earlier, we're going to show this in two parts. Sorry. As I advertised earlier, we're going to show a maximization characterization of the factorization norm in the following for the following variant of factorization norm. So B transpose CB is equal to A of 2 to X star norm B transpose times lambda max of A, sorry, lambda max of C times B X to 2 naught. Okay. I'm going to show this is equal to the maximum over PSD matrices X that further belong to the following set. So X belongs to the downward closure of the convex hull of XX transpose such that X belongs to BX of X inner product A. Okay.
What is the notation downward?
Yeah. So downward closure with respect to the positive semi-definite cone in this case of a set S is defined as S minus the positive semi-definite cone intersected with the positive semi-definite cone. That is so whenever A belongs to S and B is dominated by A, then add B to S. This is the downward closure of S. Okay. So yeah, it can be written as, so downward closure of S can be alternatively written as the union over all A in S, B at most A of B.
So just comparing this to the bilinear case, in the bilinear case, you look at all matrices. There was no PSD condition. There was, E, F transpose, right? All these matrices. You took their convex hull, and this luckily was a symmetric set, so it defined the norm, and things were there, which somehow explains the fact that we only lose a constant factor in the in the relaxation. And here it's not it cannot be a symmetric set, of course, when it's XX transpose, and these will be just PSD matrices, but you don't only take them, you take the downward closure. This is just so that, I mean, is it possible? I mean, I just wonder why it would help maximizing X times A if we take a look at a smaller matrix. Can the maximum be larger when you go down on in this?
Right. So this is a good question, and perhaps it's like, it's actually my fault for not saying it in the right order. So just as you reminded us of the following, which is that the bilinear maximum EF of A is equal to the maximum of M belongs to the hull of the EF transpose guys of A inner product M. Right? This was just taking the convex hull of the things, right? Now, on the other hand, the quadratic maximum also satisfies a similar fact because it's X transpose AX. So the quadratic maximum of A can be written as the maximum of let's say W. Sorry, no, let's use boldface X again. Yeah, X in hull of X transpose such that X is in BX of A inner product bold X. Again, this is just because I took the hull of the set that you're optimizing over. Okay. Now, as Avi was saying, this hull is actually not origin symmetric. So we don't have these nice duality properties satisfied in the bilinear maximization case. However, I do want to emphasize that what's happening here is different from what's happening down there. As in, even in the bilinear maximization case, the corresponding quantity we'll be putting here will look similar to what I'm putting here right now. So for the gamma 2 norm, what I'll be putting here will be similar to what's currently written here. So it's more about this difference between the factorization norm and what set you optimize over versus the usual bilinear maximization and what set you optimize over. So yeah, so if I removed this arrow, if I removed this arrow here, I would actually just get back the original quadratic maximization. But if I place that arrow there, I get the factorization quantity. This is the content of the theorem. So if I'm not maximizing over the hull of outer products, but I'm maximizing over the downward closure of the hull, a bigger set, now I actually get this factorization quantity. This is the content of the theorem. Okay, and a similar theorem is going to be true in the bilinear case, but we may not have time to get to it. It's extremely similar to what I'm going to show you in the quadratic case, just less clean. So this is why I just chose to show the quadratic version.
Okay.
Okay. Good. Yeah. So I'm going to show that. Right? Yeah. So let me conclude with one observation, and then we'll take a break and move on with the talk. So one observation I want to mention, and it's a trivial observation, this infimum quantity is actually equal to the infimum of W dominating A, WPSD, of the quadratic maximum of W. Okay, I'll prove this in a moment. The proof just comes from the following substitution. You just, basically, I guess you take B to be W to the negative half. Okay. I'll prove this below. So we want to show this infimum of B to the X star norm lambda max of C times this is B transpose, B X to 2 norm is equal to infimum W greater than or equal to A, W greater than or equal to 0, QX of A. Okay, and yeah, so this is going to follow from the following fact. So let's say we look at let W be PSD, okay, positive semi-definite. Then the quadratic maximum of W is actually equal to the squared X to 2 norm of W to the half, which is actually also equal by the duality I mentioned at the start of the talk to the squared norm of 2 to X star. A transpose took place, but I'm assuming W is symmetric. So the transpose is not showing. Okay. Sorry, are people able to hear the construction outside my place? I'm not sure what I could do about it, but I hope it's still on.
We hear it, but we hear you better. Well, if you had earphones, then maybe this.
Okay.
We will hear it less. I don't know.
Can everyone hear me?
I can hear you, but there's a noise in the background, but it's not too bad.
Oh, could you hear me when my headphones were on, or sorry?
We heard you when your headphones were on. I don't know if it helped with the outside noise.
Oh, I see.
Can you try it again? Just a second. The headphones.
Yeah. Any better now?
Oh. Talk again.
Yeah, is it any better now?
I don't know. Yeah, maybe people should vote.
I like the other way better, but I can deal with either one.
Okay, yeah, so you can remove the headphones. And
okay.
Fine.
Yeah. Sorry, it seems
it wasn't so
blowing.
I don't know.
Wait, oh, you like the headphones better?
No, I'm just saying I'm the only one that voted.
Okay.
I agree, Tony. I think it was better the original way.
Okay.
Whatever you're doing in the beginning.
Okay. All right. Yeah. So let's carry on. Hopefully this doesn't stay too long. Right. So okay. So let's prove this. I mean, it's very simple. So recall from definition. We have this is maximum over x and bx of x inner product wx, but that's just equal to the maximum over the same thing of x, w to the half x inner product w to the half x, which is just equal to the maximum, again, x and bx of w to the half x L2 norm square, which recall is just the definition of the x to 2 operator norm. So this is w to the half x to 2 operator norm squared. Okay. So now, yeah, I mean, armed with this fact, and also armed with the fact that if A is less than or equal to W, and W is PSD, meaning we can take negative half powers, then we have W to the negative half A, W to the negative half is less than or equal to the identity matrix. Okay, which implies lambda max of W to the negative half A, W to the negative half is at most 1. Okay, so just combining this little observation with this observation trivially yields this observation. Okay, is everyone okay with that?
Maybe you can write down the summary. I mean, I guess the whole point of this exercise was to make the duality statement you want to prove the expression on the infimum side and on the maximum side look very similar. They are both inner products with matrices. So can you write now, both of them? Right?
Yes. Thanks. Yeah. So the point was to make it look more like a convex program. So now a new goal is to show infimum W dominates A, W PSD, quadratic maximum of W is equal to the maximum bold X PSD. It belongs to downward closure of hull of XX transpose such that X in Bx of A inner product boldface X. Okay, so this is our new block. Okay. One thing about interpreting the left-hand side, okay, if W dominates A in the PSD ordering, it can be shown very easily just by staring at the definition that the quadratic maximum of W is at least the quadratic maximum of A. Okay, and so somehow the left-hand side quantity is actually saying, okay, what is the best PSD matrix that dominates A? Okay, because every PSD matrix that dominates A gives some upper bound on the quadratic maximum of A. We're saying if I take the infimum over all PSD matrices dominating A, somehow this is a good approximation to the quadratic maximum. Okay. Yeah. And in contrast, the right-hand side, instead of maximizing over the hull of XX transpose, which would give us quadratic maximization, we're maximizing over a relaxation of the hull, so the downward closure of the hull, this bigger set. Okay. With that, perhaps let's take a 5-minute break. I will start talking about downward closed subsets of self-dual cones, which is a slight change of pace, and then we'll come back to proving this.
Can I ask something about what we need to prove?
Yeah.
Is it really easy to see if we were just if A and W were just diagonal matrices? Namely, it's a question about vectors.
Right. So if W is a diagonal, if W is actually optimizing over the space of diagonal matrices, this is actually the Grothendieck setting, or rather the quadratic Grothendieck theorem that I mentioned earlier. And it's not easy. It's about just as hard.
No, I asked whether I suppose A is diagonal, so W can be diagonal. Just A is diagonal, then it should be a very simple statement, no? Or
well, yeah, if
that's with positive vectors or something.
Is A non-negative diagonal or just diagonal?
No, just diagonal. I mean, the whole point is that, yeah.
I'm not sure.
No, we'll see maybe from the proof.
Yeah. Yeah, because somehow A just ends up becoming fixed in the proof, and the key idea in the proof is introducing a new parameter, a new matrix as a parameter, and understanding how the quantity changes with respect to this matrix. And so if A has special form, I don't know how the current proof would.
Yeah, but even the statement itself, much simpler. Just the meaning of this. But anyway, yeah, why don't you go ahead and we'll see.
Okay, so before I prove the statement, I need some preliminaries. Okay, specifically, I want to talk about a different kind of polar operation that is available to us when you have a downward closed subset of a self-dual cone. Okay. Let's call this. So for the next 20 minutes or so, I'll be talking about monotone subsets of self-dual cones. Okay. So as we saw earlier, if we consider the set of matrices A such that the quadratic maximum of A is at most 1, right? This set is actually an unbounded set. However, its polar is hull of XX transpose such that X belongs to BX. Okay, so the set on the right-hand side is not origin symmetric, and the set on the left-hand side is unbounded. So in this setting, we actually don't have a bipolar theorem. Okay, so to sort of combat this issue, we actually define a new, I mean not us in our paper. I mean, I'm sure this operation is well known. When you have a downward closed subset of a self-dual cone K. So let
Vijay, just one question. So why? I don't know if you said it or not, but can you give an example where the left is unbounded? Let's say, well, when x is L infinity.
Yeah. So
yeah, it's obvious.
Yeah, it's one can take like A is equal to negative lambda times identity plus. I mean, yeah, one can just take that. For example, for arbitrarily large lambda, the quadratic maximum of A, Qx of A will be 0 always. Because it's the maximum of a quadratic form of a negative definite matrix. So
what did you mean that it's unbounded? This is.
Yeah, so the set of.
You mean, sorry, lambda can be arbitrarily large. Got it. Okay, thanks. Yeah, I understand.
Yeah.
And this is somehow that 0 is on the boundary of the polar.
Yeah.
Like 0 is not in the interior of the polar.
Yeah, yeah, and that's one boundary. Of the. Yeah.
Okay.
Yeah. Right. So yeah. So let K be a self-dual cone. Okay. So the two cones we'll be interested in today, more or less, are non-negative orthant. Which I'll use to show all the example pictures I'm going to show now, and the positive semi-definite cone, so PSD cone. Both of these are self-dual. Okay. Right. So let K be a self-dual cone. So it turns out that we can define a special polar operation, actually two polar operations, when you have a set that's downward closed and it's a subset of K, or you have a set that's upward closed and it's a subset of K. Okay. So let's define it. So given a set S, we define its polar with respect to K as just the intersection of S polar and K. Okay, which in other words is Xi in K such that Xi inner product X is at most 1 for all X in S. Okay. So we'll call this like the conic polar, let's say. Okay. Yeah, let's look at some examples. So if I consider the non-negative orthant in 2 dimensions, okay, and I have the sphere, okay, the quadrant of the disk, sorry, its polar with respect to the non-negative orthant is itself, no change. Okay. On the other hand, if I have this quadrant of the L1 unit ball, its polar is going to be the top guy. So if this is S, then this is S polar. Okay. And another example. If no, let's not do this because I don't know what it looks like. Sorry. Yeah. Sorry. Right. So there we go. Okay. Yeah, and now I want to use I want to state and use a version of the bipolar theorem that holds in this setting. So we're going to use the following fact, which is quite easy to prove using the Han-Banach theorem. I may prove it at the end if time permits, but I think this is a good fact to skip just because of how simple it is, in the interest of finishing the key ideas of the proof. Okay. So this is about polarity with respect to a cone K. Okay. If S is downward closed, sorry, convex, and closed subset of K, then firstly, S polar K is closed, convex, and downward closed. And of course, by definition, it's a subset of K. Okay. Actually, one is true regardless of the assumption on S. As long as S is a subset of K, one is true. And second, and this is where we use the assumption on S actually, the downward closed assumption on S. If we repeat this operation twice, we get back S. Okay, so this is a bipolar theorem for conic polar.
So can we look at the picture, the two-dimensional picture there?
Yeah.
So the part of the disk, this returned to itself, that was no problem. But when it was the just this lower triangle, which is part of the L1 and L1 ball, you took the this special polar with respect to the first quadrant, and you got something bigger.
Yeah. And when we take it again, we get back S.
So it can get bigger or smaller.
Yeah. And in general, what will happen, I mean, assuming it has the same 2 points of contact as the sphere, so if I have a general curve like this, it will become something like this. And vice versa. So it kind of gets reflected across the sphere surface.
Okay.
Okay. Yeah. And actually, more generally, for a generic set S that's not downward closed, S polar K is equal to the downward closure of S. Okay, I'm not going to use this fact, but I'm just stating it for your convenience. And just to show people another example, so in the non-negative orthent, what I mean by the downward closure of, let's say, this petal is this guy. That's the downward closure of the petal. Is there an issue?
Is that true? So the, I see, yeah, okay. Just most of it just comes from.
Yeah, the tip, I guess. I may have drawn it wrong.
You do have some rounded bit, right? Like you should have some.
Yeah, definitely. Yeah, sorry. Okay, maybe I should redraw it. That's how it looks. Okay. In other words, down S, as I said earlier, is equal to S minus K intersection K. So in this picture, that corresponds to S minus K will be this infinite region. And then you take the intersection with the non-negative orthent, and so you retain only this region. Okay. So that's one fact. Okay. Now we're just going to do the same thing, except we want to develop this for upward closed sets as well. Okay. So I'll need another fact. For upward polarity. Okay. So we define for a set S an upward version of the polar as the set of vectors Xi such that Xi inner product X is at least 1 for all X in S. Okay. And Yeah, and if S is closed, convex, and upward closed subset of K, of a self-dual cone K, then firstly, S polar is closed, convex, and upward closed subset of K. And secondly, S polar is equal to S. Another version of the bipolar theorem.
So somehow you omitted here the dependence on K in the polar notation, but it's implicitly there.
Actually, that's a good observation. For this polar operation, the operation doesn't depend on K. The theorem, however, does. You need some self-dual cone K to contain the set S.
I see.
Yeah, it's a strange difference between downward and upward, which I can't quite point to. Yeah. Okay. Okay, good. So that's basically all we need from this. Yeah. So what I wanted to emphasize is that, you know, all the duality statements and all of the factorization theorems I mentioned, and in fact more that perhaps I haven't shown, I think basically come down to this bipolar theorem for a downward closed or an upward closed set. Okay. And it turns out that this observation appears in 2 or 3 different ways, and in each of the proofs of all of these factorization theorems. Perhaps more souped up versions of them, but this is what I think is inherently going on. So this like duality of downward closed set seems pretty fundamental. Okay. So equipped with that, let's make an observation. The observation is that the downward closure of the hull of XX transpose such that X belongs to BX is the polar of this set is the set of PSD matrices that have bounded optimum. Okay. This follows from definition. Recall Qx of W is equal to max X in BX, W inner product XX transposed, right? Yeah. So yeah, I mean, let's prove it. So consider any X in, let's call this S1. Okay. Then by definition of downward closure, there exists Y belonging to the hull of XX transpose, such that X is in BX, such that Y dominates X. Okay. Now consider any W inside, let's call this S2. Then for any W inside S2, W inner product X is at most W inner product Y, because both are PSD. Right? This is heavily using the fact that W is PSD, which is at most 1. Because Y is a convex combination of unit vector autoproducts. Okay. So therefore, X is in the polar of this set. Okay. Oh, sorry, I made a notational mistake. Yeah, I meant polar with respect to the PSD cone, which I'll denote by S plus N. Okay. Yeah. Now applying the bipolar theorem, we obtain that the downward closure of the hull of XX transpose, set X and BX, is equal to the set of bounded, the polar of the set of bounded PSD forms. W at most 1, polar S plus N. Okay, this follows from applying the bipolar theorem, like and taking the same polar operation on both the left-hand side and right-hand side of the above inequality. Okay. So yeah, I mean, this is actually one reason why this downward closure of the hull of XX transpose comes in. It's actually the polar of the set of bounded PSD forms. Okay, so it comes in a very natural way. Okay, and one consequence of this I'm going to use, it's not hard to prove just from what I've already said, is that if X belongs to the boundary of the downward closure of the hull of XX transpose, I'm not going to write the entire thing because I've wrote it like 3 times, then there exists W that's PSD such that X inner product W is equal to the quadratic maximum of W. Okay, or another way of saying this is there exists W that's PSD and has quadratic maximum at most 1, equal to 1, and moreover, the inner product of X and W is equal to 1. Okay, this just follows from the fact that they're polar to each other. Okay. But really, yeah, I will use this fact. So if X is on the boundary, then there exists a witness W. So if I have any distribution over, so if I'm in the downward closure of the distribution of, downward closure of the hull of outer products, then there is an instance W that witnesses this.
Okay. Vijay, can I ask a question? I'm just trying to just understand this at some higher level than the formula, just comparing it to the usual case where we have a polar, right? Where we have a symmetric, centrally symmetric set of some norm. I guess there, we don't need to take downward closure because it comes automatically from the symmetry of the body. We have, right? I mean, we have all these elements because we have the minus of the, so, and then we can use just convexity, some Hahn-Banach theorem, right? Convex duality.
Yeah.
And this exercise seemed to replace it in the case of this conic duality. I'm not sure how you call it, right? This exercise allows us to think of the polar definition here when our set is contained in such a self-dual cone. The self-duality of the cone allows us to just do it with this cone not changing, right?
Yeah.
And just allows us to move one downward closed set to another downward closed set that's in the same cone.
Yeah.
And then come back to it. So, and what you are proving now is, so the analog, or what you will be using now is, maybe you'll prove it, is some analog of the Hahn-Banach theorem, of the duality.
So I
use here, right?
Yeah, so Hahn-Banach theorem is used in this bipolar theorem, in the proof of this bipolar theorem, and it's quite simple and straightforward, and it's like I mean, it's mostly just, it's 5 lines, but yeah, I just may not have time to go over it.
But it's similar to the, I mean, but similar to the original one once you have the definition set up so that it will apply.
Exactly. Yeah. You just need to make an additional observation about the hyperplane that you get from Han-Banach, that it must be in the cone K. And yeah, that's about it. And then it all falls out from there. Yeah. Yeah. Right. So, okay. Yeah. So now we finally see where this downward closure of the hull comes from. It is the sort of conic polar of the set of bounded PSD forms. Okay, so up here in this program that you saw, right? The objective is the quadratic maximization of a PSD form, and that has become a constraint after getting polarized. Okay, so this should be familiar to people who've seen convex programming duality before. Okay, so yeah, so given scarcity of time, let's jump into the proof. Okay. All right, yeah. So the main idea that's left that I haven't shown yet is this idea that comes from Lagrangian conic duality, and the idea is to actually parameterize the infimum I wrote earlier by yet another matrix, okay, and study how it changes with respect to this matrix. And it turns out that the study of this, of how it changes with respect to this matrix, leads to nice developments. Okay, so let's.
Sorry, what are we left to prove now? I mean, given this setup,
we're still left with the original thing that we wanted to prove, which is that infimum W greater than or equal to A, W PSD, quadratic maximum of W must be equal to maximum of X inner product A. X belongs to downward closure of hull of XX transpose, such that X and PX. Okay, we're still trying to prove this, right? But first, we're going to parameterize this quantity by yet another matrix. So we're going to define a new quantity omega of M as infimum QX of W, such that W dominates M plus W dominates A, and W is PSD. Okay, and I allow M to be anything in Rn cross N. Any symmetric matrix. Okay. Right. So two observations. Omega is convex. Okay. This follows from the fact that we are minimizing a convex function over a convex set. Okay. And the second observation is that omega is decreasing in PSD ordering. That is, if M1 is dominated by M2, then omega of M1 is less than or equal to omega of M2.
Yeah, we really want omega of 0, right? That's what we want.
Yeah, exactly. Good point. Yeah. So right. As Avi said, this is equal to omega of 0. Okay, so we want to show that this maximum is equal to omega of 0. Okay, the 0 matrix. Yeah. Okay. So omega is convex and omega is decreasing. Okay, and now we can look at the epigraph of omega. So let's look at the epigraph of omega. Okay, so I'm going to kind of do a sort of proof by picture a little bit. So think of the lower axis as Rn cross N. Okay, so M is this lower axis. Okay, and we think of, let's say, Z in R as the vertical axis. Okay, and just recall the epigraph of a function is, and in this case, the epigraph of omega is the set M comma Z such that Z is at least omega of M. Okay, which in other words is yeah, it's the set M comma Z such that there exists W, that's PSD, and W plus M dominates A, and quadratic maximum of W is at most Z. Okay, so this is the definition of the epigraph of omega. Okay, but really you should just think of the picture. So this is, I'm just plotting omega of M. Okay, and let's say this is the point M equals 0. Okay, right now, yeah. Sorry, before I say anything, I should tell you how I'm going to prove this above inequality. So first we prove that the left-hand side is at least the right-hand side. This is very easy. This is weak duality. And then we're going to show that it holds at equality by exhibiting an X. So we exhibit X such that X inner product A is equal to QX of W. We exhibit X and W such that X inner product A is equal to QX of W. W is at least A, and W is greater than or equal to Z. Okay, or in other words, we exhibit an X, of course, in this feasible region, such that X inner product A is equal to omega of 0. Okay. Yeah. So yeah. Okay. Let me first show the inequality, and then I'll show you how to exhibit this X. Okay. And the way I'll exhibit this X is by doing some hyperplane separation argument on this curve here. But yeah, I forgot to show you the trivial inequality, and let me show that first. Okay. So let X belong to downward closure of hull of XX transpose such that X is in BX. Okay. And let W be such that W dominates A, W is PSD, right? Then X inner product A first you want to say there exists Y dominating X such that Y is in hull of XX transpose. Okay, this is just the definition of downward closure, right? And now X inner product A is at most X inner product W. This is because A minus W is negative definite, which is at most Y inner product W, using the fact that Y, X and W are all PSD, and Y dominates X, which is at most 1, because Y is a convex combination of outer products. Sorry, which is at most, QX of W. Okay, so this implies the inequality I promised above, that the right-hand side is always at most the left-hand side. Okay, so now we're going to show equality, and the way we show equality is by just exhibiting blackboard bold X such that X inner product A is equal to omega of 0. And of course, X must belong to the downward closure of the convex hull. Okay. Right, so let's do that. Yeah, so again, going back to this epigraph. So we define this function omega, it's convex and decreasing, right? And then we can look at its epigraph. As a consequence of it being decreasing in the PSD ordering, it's actually upward closed. Okay, so it's upward closed. Okay. Yeah, this is a fact we'll use shortly, right? Now, we look at the point m equals 0, right? And we look at this point here. We look at this, what's going on? Yeah, we look at this point here. Why is my iPad misbehaving? Okay, we look at that point, right? And since the epigraph is convex, if and only if a function is convex, the epigraph is convex, and there is a tangent we can draw at that point that lies entirely underneath the epigraph. Okay. So in other words, there exists a point x comma z naught such that x comma z naught inner product with m comma z is greater than or equal to omega of 0 for all m comma z belonging to epigraph of omega. Okay. Now by some trivial observations, we may assume z naught is equal to 1. Okay, just allow me to make that assumption in order to proceed quickly with the proof. Okay, so we have x comma 1 inner product m comma z is at least omega of 0. Okay, so x inner product m plus z is at least omega of 0 for all m comma z pairs inside epigraph of omega. Okay. Yeah. Now we're going to show that this x that we got is the desired x. Okay. So the first observation is that x belongs to an appropriate scaling C of the polar of the epigraph, the upward closed polar of the epigraph. We call that I define the upward closed polar as a set of vectors that have inner product at least 1 with every guy inside the set. Okay. So just by the above thing, we get this, right? And recall, yeah. Recall I said that if a set is upward closed, then its polar is closed, convex, and upward closed, and a subset of the self-dual cone K. Okay. So basically, from that observation, we actually conclude that X must belong to the positive semi-definite cone. So X is PSD. Okay. I can actually prove it here if people are not happy with how quickly I went over that. Okay. Yeah, so basically, if X does not belong to S plus N, then there exists W prime, that's PSD, such that X inner product W prime is negative. Okay. And then you just take M, like fix any M comma Z that belongs to epigraph. And instead consider M plus lambda times W prime for a very large scaled W prime. Because epigraph is upward closed, M plus lambda times W prime is still inside this set. Okay. And so this will contradict the fact that X needs to have, large inner product with this matrix. It will actually have large negative inner product with this matrix. Okay. So yeah, so in other words, X is PSD. Okay, I'm going to erase this. Okay, so X is PSD. Great, right? Now what are we left with showing? Well, we need to show it's in the convex hull of outer products, right? And finally, we need to show it has good objective value. We're going to show both in one shot. Okay. So the way we're going to show it is this. Claim the infimum over PSD W QX of W plus A minus W inner product bold X is equal to omega of 0. Okay. And I'll prove this claim below the fold, but first I will show how once we prove this claim, we are done. Okay. So we're going to show claim 2 that infimum of W PSD QX of W plus A minus W inner product bold X. By the way, an important thing to keep track of here is W is now a generic PSD matrix. It doesn't necessarily dominate A. Okay. This infimum is equal to negative infinity if bold X is not in the downward closure of the convex hull. And it's equal to A inner product bold X if X is in the downward closure of the convex hull. Okay. The proof is the following. Okay, so let's just rearrange the expression. So we have QX of W minus W inner product X plus A inner product X. And then we have infimum WPSD. Okay. So basically we're going to analyze when can we drive down this quantity to negative infinity and when can't we? Okay. So if there exists W such that QX of W is less than W inner product X, then by just scaling W, we are done. We can drive this to negative infinity, right? So yeah. On the other hand, if there doesn't exist any such W, we can substitute W is equal to 0. Okay, and if we substitute W is equal to 0, we get just A inner product bold X. Okay, so I'm going to say more about this, but I just wanted to point out that the two cases we are looking at is if there exists such a W such that this inequality holds, then we can drive the value down to negative infinity. And if there doesn't exist such a W, we can achieve A inner product X just by substituting W is equal to 0. Okay. Right. So let's see what happens when Qx of W is less than W inner product X. Sorry, I already said what happens when that happens. So I mean, if Qx of W is less than W inner product X, we can just scale W arbitrarily, and this infimum will be 0, right? On the other hand, if it fails, I need to show you that that the value is equal to A inner product X, right? So let's say that that condition fails. That is, for all W that's PSD, Qx of W is at least W inner product X. Okay. Well, this is actually saying that X inner product W bar is at most 1 for all W bar in the set of bounded PSD forms. Sorry, less than or equal to 1. Okay. So therefore, X must belong to the conic polar of that set. So X belongs to the downward closure of the hull of XX transpose such that Xn Bx. Here I use the fact that we showed earlier that this set is the conic polar of the set of bounded PSD forms. Okay. So once we obtain this fact that X is in this hull, well, we can check that this expression is always non-negative, and equality is achieved when we substitute W is equal to 0. So we have proved this fact that I claimed. So we have proved claim 2. Okay. So now, now let's go back to claim 1. Okay, why are we done after claim 1 and claim 2? Okay, by claim 2, recall we found this bold X earlier from analyzing the epigraph and looking at the hyperplane. We found this bold X, right, that satisfies this. Okay, and yeah, and by claim 2, since omega of 0 is not negative infinity, it must be that A inner product bold X is equal to omega of 0, and moreover that X belongs to downward closure of hull, right? Because it can either be negative infinity or it's A inner product X, and since omega of 0 by definition, by the original definition, is not negative infinity, it must be that A inner product bold X is equal to omega of 0, and that X is in the downward closure of the convex hull. This bold X that we obtained from the hyperplane. Okay. So given claim 1, let's say, we are done. Okay, we have constructed our final X. It has good objective value. It is feasible, like it belongs to the downward closure of the hull, and we're finally done. Okay. Now we need to prove claim 1. Okay, claim 1. I'll try my best to finish this in 5 minutes. Sorry for going over time. Okay, so claim 1. Yeah, let's just remind you what I wrote. Yeah, infimum WPSD, Qx of W plus A minus W inner product bold X must be equal to omega of 0. Okay. Proof. Right. So let's start with the infimum of M comma Z in the epigraph. of omega of z plus m inner product fold x. Recall, this is equal to the inner product of those two vectors. Okay, the vector m comma z inner producted with the vector bold x comma 1, the hyperplane that we got, the tangent hyperplane. Okay, now recall this just by construction. So by construction, the inner product with the tangent hyperplane is minimized at this point. It is minimized at m equals 0. Okay, just putting that out there. Anyway, so now we're minimizing the tangent hyperplane over this epigraph. Okay, and of course, this is at most the infimum. Of WPSD QX of W plus A minus W inner product fold X. The reason is we may substitute M is equal to A minus W. Okay, in the definition of omega. Just to remind people the definition of omega of M is infimum of QX of W such that W plus M is at least A and W is PSB. Okay. So taking M is equal to A minus W and Z is equal to QX of W is always a valid choice of parameters. Okay, so these points M comma Z of this particular form are always in this epigraph. Okay, so now since we're taking an infimum over a smaller set, the first inequality follows. Okay, I'm going to erase what I wrote below. Okay. Now this in turn is at most the infimum of WPSD, W greater than or equal to A, QX of W. Okay. Why is this? Well, restricted to the set of instances where W is greater than or equal to A, restricted to this set, this quantity must be negative. Right? Because X is positive semi-definite, as we concluded earlier. Okay. And then we're taking an infimum over a smaller set. Sorry, we're taking an infimum over a smaller set. So not only are we taking an infimum over a smaller set, we're also changing the objective to something that's larger. So this inequality follows. Okay. But recall, this is our original quantity. This is omega of 0. This is the left-hand side of our convex program, equality. Okay. Right. But on the other hand, as I told you, we were minimizing the tangent hyperplane over this epigraph, and the minimum happens at this point, and the value of the minimum is equal to omega of 0 by construction. So we started this infimum actually with the following equality: omega of 0 is equal to the infimum of the tangent hyperplane over the epigraph. So we have this chain of inequalities that start and end with the same thing. Therefore, we have proved the desired equality. Okay. Yeah, this ended up being a lot less intuitive than I envisioned. But I really hope people take home the message that to prove a factorization theorem, there are two components: an algorithm based on rounding Gaussians, and a duality theorem that relates an infimum factorization norm to a maximization optimization problem. Great, that's it.
Thanks, Vijay. So yeah, let's see. I mean, so we can. Will you come here at 1:30, Vijay? Or,
So Yeah, the friend I went with tested negative for COVID, so it's.
No, not here. I mean, will you be in the group meeting to answer more detailed questions? So let's ask for
Sure,
people
yeah.
who have general questions, and then if people have detailed questions, they can interrogate Vijay later or even later.
Sounds good.
So questions.
So Avi, you might have asked some version of this earlier, but for these sort of upward closed downward, or yeah, upward hull, downward hull sets.
Yeah.
How important is it that the cone you're using is self-dual as opposed to just using a cone and it's dual, like in the appropriate? I can imagine, you using a cone and possibly it's different dual in the appropriate places and then hoping for similar things.
Yeah, it's a good question. I need to check many things, but I don't think it's extremely important. But at some point, you'll be comparing two matrices, one of which belongs to K and one of which belongs to K star. And you'll be comparing them with respect to the ordering induced by K. And this is weird for me, which is why everywhere I just instantiated it as self-dual. But I think it still works because like this conic Lagrangian duality is stated actually for like non-self-dual cones.
Yeah.
But again, like so many things have to go right. So I mean, as much as I say that this is conic Lagrangian duality, like a lot of the science happens in instantiating conic Lagrangian duality on these like special sets, and they have enough structure that more magical things happen. So I don't know what else might break down if you take away self-duality. I need to check. There were like 4 or 5 things that I would need to check.
I mean, you have a nice self-dual cone, so in some sense.
Yeah. PSD appears everywhere, and in the growth and Deke setting, it's the non-negative ortho. That is the cone being considered.
Just a comment. I mean, I think it's really valuable for conveying intuition about what's going on, to consider the case that A is diagonal, A the input. I mean, so your quadratic optimization is just inner product with this sum of squares, right? Weighted sum of squares of them. Right. I mean, I think that all the concepts that come up. I mean, you also have the non-negative ortant as your cone, and so I failed to get the intuition for why we need to actually invent this parameterized space omega. I mean, sort of in a linear program, you're sort of allowed to relax the right-hand side in some sense, so this trick, its value, it appears, of course, in the proof, but so I'm not sure I understand why. I mean, why it has to be there. But anyway, that's maybe that's.
I mean, I've actually tried to circumvent it because it was bothering me, but I haven't succeeded.
Okay.
But however, the diagonal case, I think this is worth thinking about. I mean, at least the non-negative diagonal case will be trivial for some reasons.
No, not non-negative.
Yeah. So the next.
I mean, of course, but you want to add a positive vector. It's. I mean, I think everything will become simpler, and maybe all this. Maybe the intuition will become. Simpler. I hope. I don't know.
Yeah, like my one worry would be that like the best thing to do in the in the diagonal case would be that you take W as equal to the positive diagonal entries and 0 on the negative ones or something like that.
Well, that's essentially what happens also. In the matrix case, in some sense, this happens too. It's only in the PSD ordering. I mean, I don't mind that it's solving it's not about having an easy solution to the quadratic optimization. We know how to do that. That's really easy.
Right.
I'm talking about the proof of duality, which is not obvious to me. Okay, more questions. All right, so those who want will come back at 1:30.
Thanks, everyone.
Thanks, Vijay.